So, hi everybody. So it's my pleasure to start the second day of CoNEXT with a great keynote by Adrian Perrig. So I'm gonna just briefly introduce him and then let him the floor. So probably most of you know Adrian is a professor at ATH. He's been serving also as technical director of Carnegie Mellon Cybersecurity Lab. Now he's a distinguished fellow there. He has earned his BSc in APFL, then went to CMU for a Master in Science and PhD, was visiting Berkeley. He had a lot of achievements. I mean, I'm going to just mention a few of them, like the CIGSAC Outstanding Innovation, the IEEE Symposium on Security and Privacy Test of Time Award. He's a fellow at IEEE and ICM, and he's best known for activities on SCION. That is going to be the main topic of the talk of the keynote today. So thanks very much, Andrew, for joining. The floor is yours.
Yeah, thank you so much for your kind invitation and introduction. Okay, it's my great pleasure to give this keynote lecture on the SCION Research and Education Network. This is actually mainly also driven by David Hausherr at Magdeburg, and I'll be talking more generally about SCION during the talk, but in the end of the presentation also cover this Research and Education Network. All right, so to start with, here's a picture of the internet by the OPTI project. We have billions of hosts. We all know this infrastructure quite well. We're all doing research on this. We're contributing to the internet. And here's a animation also by the OPTI project. So we see how the internet evolves. So it kind of looks like an organism. I thought this was quite interesting. And what's definitely also interesting about the internet is that it's, despite its growing size and growing use cases, it still works pretty well, right? So we all use this every day. But as researchers, we always try to see how can we improve things. We've seen a lot of issues in the internet dating back to the last century, where people have noticed a lot of security issues of today's internet. And so this was also the beginning of the SCION project, when in 2009, we looked at how secure can actually a global internet be. So this is not the question about an intra-domain network, but really for an inter-domain network, how do you construct such a highly secure network to achieve security against attacks, resilience to failure, and also improve scalability compared to the current internet. So these are challenging questions to answer. Of course, security needs to be well defined. I mean, there's so many aspects to security, but we looked at this from a very general perspective when we started on this project in 2009. So we called the project SCION, and SCION actually, so it's an acronym for Scalability, Control, and Isolation on Next Generation Networks, but it also has another meaning. And the other meaning is that it means a descendant of a wealthy or aristocratic or influential family, or also sometimes you refer as a sign as the heir to the throne. And this was, we thought this was an interesting name in the beginning. And so with respect to this name, you can also think about if SCION is the heir, then who actually are the parents of SCION, right? So thinking about this a bit, so looking at the SCION as an offspring, so who could the parents be? So clearly one of the parents is the unreliable and insecure internet, right? This has created a lot of projects that try to succeed the internet. But then the next question is, well, if one of the parents is the internet, then who is the other parent? So when you look at SCION, some people think, well, secure routing or source routing would be one of the parents, or censorship, or some people have these kinds of interpretations, but this is not the case. It's SCION does not use source routing, as we're going to see in a minute, based on depending how you look at source routing, but I'll be talking about this in a few slides. But rather, the candidates we see as having influenced SCION and being potential parents include transparency, security, path-aware networking, open source, sovereignty. So these kinds of concepts of an open, transparent, and secure internet. So there have been a lot of projects, and a lot of projects that try to reinvent the internet and looked at next generation architectures. And many of them could be seen as potential parents or siblings. And in particular, the ones shown here in red and here the NERA project and HAIR project were particularly influential and have similarities to the SCION project. But we look at these more as siblings rather than parents in their own right. So to think about which entities could have been a parent, I'm going to take a journey through the different attributes of SCION to identify who the other parent could be. And SCION has been a long-running project, so there's many aspects to it, but I thought these 5 attributes are particularly important. And the first one being governance domains to make trust more scalable, and also the scalability of the system itself, of the path discovery and path dissemination to achieve rapid global connectivity. Then also the massive multipath that enables fine-grained path optimization. From a security perspective, the high-speed packet authentication in the network, and that also enables path validation, is quite distinctive. And finally, I'll be talking about some real-world deployment incentives and use cases. So please follow me on this journey. We'll look through these 5 aspects. And the first aspect of these governance domains of making trust more scalable stems from the issue that trust is inherently unscalable when you expand the number of entities that need to have some common trust. So we see this in the internet. As the internet has expanded, the kind of systems that we've been using, like the monopoly infrastructures or the oligopoly infrastructures for trust. So monopoly meaning there's a small number of roots of trust the whole world needs to rely upon. And in the oligopoly model, you have a very large numbers of trust roots that all need to be trusted. And that's the case in the TLS PKI, where you need to trust all these entities, all these certificate authorities, public keys, essentially. So when you look at these kind of models, you see it's very challenging to scale them to very large networks. Of course, we're making use of these infrastructures, but the problem is that they have single points of failure, right? If the one root key in a monopoly type trust infrastructure is compromised, essentially the entire system becomes insecure. But also in the oligopoly in TLS, we've seen CAs that got their private keys compromised that could then issue bogus certificates. Of course, the research community has dealt with this also for many years with many approaches. But the question is, how can we fundamentally scale trust in a global environment? This was actually one of the first questions we tried to answer in SCION, and that's for this, to enable this trust scalability, we introduced isolation domains, and the name is supposed to mean isolation of faults, but not isolation of traffic. And so the isolation domain is a grouping of autonomous systems. So what we see on the slide here are 5 isolation domains, and the smaller circles represent autonomous systems like in today's internet. So the structure of the internet stays the same. We have the same connections you have today between autonomous systems. So you have tier 1 ASs or the ASs that create the global connectivities, but then also leaf ASs or the more local autonomous systems are represented by these smaller circles here. So in SCION, these entities then group together to form an isolation domain and establish the trust root configuration, this TRC. So this is essentially a definition of the roots of trust that are being used in this isolation domain. So you can see that it's a virtual concept. So an entity can belong to multiple of these ISDs. And essentially, the routing system then is going to find paths across and within each ISD, as I'm going to show in a second. So this structure was introduced from a trust scalability perspective, but it turns out it was also very useful then to make the whole routing systems more scalable as well. So the observation that we now have, literally 14 years after having made this suggestion, is actually these isolation domains, or you can also think of them as governance domains. They're really quite powerful. And they actually, as we're going to see towards the end, they have driven the first use cases and the first adoptions of SCION. And so again, these governance domains enable the local definition of trust roots and also the trust policy. And this then scales because it's a local definition. What's also an important aspect is compliance. And we've talking to practitioners who run networks these days, they find that compliance with government regulations has become a big challenge. And they see that these governance domains or isolation domains in SCION enable the definition of the local regulations and then the control, how traffic flows to be able to comply with different laws and regulations. So they see this as a big advantage of using SCION. So then we'll also see that the hierarchical routing that comes out of these isolation domains also increases scalability, as we're going to see in a minute. And yeah, the point I want to make is also the internet structure actually is quite similar in the sense that we have ISPs that tier 1 ISPs that form the global connectivity, and then the more localized ISPs that provide the local connectivity. So this actually fit quite well into this model, and we see these isolation domains are now forming across the world with entities then taking their respective roles. Right? So that's the first part. So before I go into more details, let me quickly give you an overview of the SCION architecture. Then I'll go into more details later, but I think this overview will help to see how the pieces fit together. And so here we see 3 isolation domains, and in the control plane, SCION finds path segments, and these path segments, we'll see in a minute how they're constructed. They're being disseminated through a path server infrastructure, and end hosts then want to communicate, fetch these path segments to create end-to-end paths. So the architecture is made in a way that there is always a path. There is always a combination of these path segments that gives you end-to-end connectivity. And in this example here, we have a host in F who communicates with another host in S. It asks the network for these path segments. It says, I want to communicate with S, which path segments can be used, and the path server infrastructure provides, in this example, these 6 path segments, which then enable 2 different end-to-end paths that can then be placed in the packet header along with security and cryptographic information that prevents alteration. And then the packet will follow these paths. Right? That's why some people think it's source routing, but source routing has 2 aspects. One is the discovery of the end-to-end paths, and one is the traversal of the network itself. And SCION, some people could say it is source routing because the path is in the packet header, but the way I prefer to look at source routing is really how is the path being discovered. And here the sender cannot just pick arbitrary paths, right? The sender doesn't have the internet topology. The sender just obtains these path segments and can combine them and figure out which ones give you an end-to-end connection. So in that sense, SCION is not a source routing architecture. So what's an interesting aspect of SCION also is that the routers become stateless. So there is a server infrastructure that's handling the control plane and all the resource-intensive aspects. But really in the forwarding plane, SCION is extremely lightweight. offering extremely efficient forwarding despite the cryptographic operations, as I'm going to show in a minute. And so the routers are pretty much stateless entities without any intradomain forwarding tables, and simply follow the instructions in the packet header. I should also say that there's a workshop on Friday by Lars Christian Schulz, who's here to discuss also SCION and P4. So just as an advertisement to where the forwarding plane is being looked at and how to make that more efficient using P4. All right, so let me dive into a bit more detail how SCION actually works, and I'll just provide an overview of the routing itself for the most part, and without going to the details of what's really in the packet header. So in essence, the core ASs and the core ASs are the ones that manage the isolation domains or this governance domain. They issue what we call beacons, path construction beacons, or PCBs in short, that explore path segments within this isolation domain. And only the core ASs issue these beacons, which actually contributes to the scalability of the system. And so we see different path segments that are being created. The same thing operates between core ASs, and so there is a beaconing finding path segments between all pairs of core ASs, and we see here a bit more detail what's in these beacon messages. So it has interface identifiers. These are interfaces between the different autonomous systems. And also then the hop fields, which is the information that then goes into the packet header for the data plane. So they're constructed, it looks similar to BGP actually at this level, but it has a lot of additional security information. You could say similar to BGP SEC if you wish, that identifies these path segments. So here's the same process as an overview with the tracing of these paths of an announcement by T, different PCBs to identify these path segments. So they're being distributed. So they're being created through this beaconing process that happens periodically, but then they're being disseminated through a mechanism that's similar to DNS. Path servers that are in each autonomous system store these path segments, and then clients and hosts pull these path segments when they would need end-to-end paths. So for example here, when we're at the leaf AS, the up path, so up visually going towards the core, are paths to get towards other destinations. And so locally, the different path segments are being analyzed, and locally there's a decision being made which path segments are being shared with the local hosts. And in this example, all these path segments are being shared, and they get registered at the local path server for local hosts to look up. But what's perhaps more exciting is that one can also control how others reach you. So this is called ingress path control. So there's the path segments that are being disseminated to other entities that want to communicate with you. So in the core path server, one can register also these path segments and select which ones are being registered and which ones are being dropped. So in this example here, one path is being dropped, depending on whether it's a suboptimal path or it's a path you want to keep for special purposes or something. But the paths are then being registered to reach you. SAM provides some control for doing that. And that's actually quite a powerful feature that you can use at this level. Right. So this beaconing process, what was surprising to us is how efficient it actually is, and the scalability we compared to the skills to the effort BGP is performing. And what this diagram shows is we took different autonomous systems and looked at the BGP messages they process. And here, each bar represents one of these autonomous systems, and we compared how much work CION is doing for providing connectivity. And this is for intra-ISD beaconing, so for the local beaconing, and that's extremely efficient, where CION only performs on average 1.5% of the work BGP is doing, except CION finds a lot more paths than the BGP single path exploration, right? Where BGP in the end has one path, but in this case, CION can find already a dozen different paths depending on the topology. But the point here is intra-ISD beaconing is extremely efficient, on the order of 1 or 2% of the effort BGP is performing. The core beaconing requires more effort because every core AS beacons to every other core AS to find path segments. And here, the overhead is quadratic, of course, in the number of core ASs. But simulating 2,000 ASs, the 2,000 most connected ASs in the internet, we find that the effort of CION is roughly 10% of the effort of BGP, whereas CION finds 20 to 60 different paths doing only 10% of the work. The difference is even more striking when you compare with BGP-SEC. So on the diagram on the right, you see CION in blue with the effort normalized to BGP, normalized to 1. BGP-SEC on average requiring about 5 times the overhead of BGP. And so then obviously the scalability of CION becomes even more apparent because it also has even stronger security properties than BGP-SEC. So we published this 2 years ago here at CoNEXT in this paper that documents all these evaluations. So with respect to scalability, this is actually quite exciting because how come that CION is so much more efficient? And there's 3 main reasons for this. So first of all, CION is performing AS level routing and not IP prefix-based routing. We know some ASs have large numbers of IP prefixes, and so this already cuts down the effort quite dramatically. But perhaps the main reason is that leaf ASs don't send out any of these beacon messages themselves, right? They only receive beacons, and the majority of autonomous systems in the internet are leaf ASs. And so this dramatically reduces the overhead. So the leaf ASs, they only register their path segments, but the registration is a unicast message, or is a unicast-based operation that is not broadcast to the whole world. And so this is probably the main reason why CION is so efficient. Another reason is that there's no iterative convergence. So as we know, many routing protocols perform an iterative process to find short paths, but this is not being done in CION. So over time, if you let CION run, the CION beaconing run over time, it just finds more and more different paths. But the basic connectivity you reach almost instantaneously because the system prioritizes beacons to new destinations that have not yet been seen. So if you look at cold booting the internet, which some people believe would take over 24 hours, perhaps 48 hours for BGP to converge, in CION you can really reboot the internet and within seconds have global connectivity thanks to these mechanisms. So the next point is about multipath. And here, I believe many people in the audience are excited about multipath. And I just want to first motivate the importance of multipath. And so we looked at, for instance, a connection from Zürich to Singapore. And typically there are 2 paths to reach Singapore. One is via the US, and the other one is via the Suez Canal, with a difference of 200 milliseconds. So the Suez Canal connection is almost twice the speed than, or in terms of latency, than going through the US. But if you look at bandwidth, actually, the cables going through the US offer higher bandwidth, and so typically the US path is being preferred with the high latency. But obviously, if you have, say, a video conference, you'd like to have the audio signal go over the low latency path, the video signal going over the high bandwidth path. And so you'd like to use both, right? Neither path is really better than the other. So in a multipath system, you can then make use of these different paths that are available and also optimize your communication accordingly. What's really exciting, and we're actually seeing this in the SCION production network, is that there are really a lot of paths that SCION can make use of. So in this example here, we have a number of different core path segments, and also several intra-ISD path segments. And when you combine them in this example here, you have 54 different paths from S to D. Of course, many of the links appear in several of these paths, but overall you have 54 distinct paths. We did a measurement in the SCION production network, and from the ETH, we looked at all the paths to different other ASs that are on the SCION network. And so we picked a number of these ASs, and here's the result, which was really quite surprising, actually, that some ASs have 240 different paths already. And we see that the least number of paths was 4 to the AS with the least number of paths. And the median was 120. So there's a lot of entities. It, of course, depends on the topology, how many paths then become available. But it was quite surprising to see this diversity on the current production SCION network. So we find this is a really exciting opportunity to have dozens, or in some cases, even over 100 different paths available for optimizing your traffic. And in particular, if you look at different metrics, say you look at latency or jitter, or the bandwidth achieved, or you have some privacy or anonymity preferences that where you want to direct your traffic through different areas, or you want to optimize for CO2, or you want to optimize for jurisdiction and so on. I mean, people have a lot of different possible type of metrics they want to optimize. And once you have a very large number of paths, it's likely that then the best path that people want is part of that set. And so this is really exciting and actually opens up a lot of research opportunities for figuring out how to improve the beaconing further, how to distribute perhaps the paths or path information in a better way. Because actually when you have, say, 200 different paths, you cannot measure all of them to find the best one. It will take you too long, right? So it's an exciting research opportunity to figure out what type of information should we add to these paths, and how do we update it, how do we disseminate that information to take advantage of this huge path diversity. And so we see that applications that make use of a lot of different paths then also can, and they continuously optimize their paths, we see that they can actually achieve also higher performance thanks to that. The next point I want to talk about are the cryptographic aspects. And here, what's always very exciting to me is how to do things at very high speeds. So in particular, how to achieve packet authentication or also path validation at almost no cost at line rate. And so designing secure networking protocols for over 20 years now, it was always a big dream to being able that the router can authenticate the source address, for instance, and many of the security problems can be solved if source IP spoofing is not possible anymore. The question is how to design a system that enables per packet source authentication at a speed of a few nanoseconds to make it practical on a hardware router. And so for this purpose, we've designed a system called DRKey, which stands for dynamically recreatable keys. which enables exactly this property that a router can derive a key for any host on the internet within a few nanoseconds. So even in software, this only takes roughly 20 nanoseconds. So this DR key system, the idea is to have use an efficient pseudorandom function to locally derive the keys at very high speeds. And the pseudorandom function, you can instantiate that simply with a block cipher. So for instance, AES can be used to instantiate such a PRF. And so for example, an AES would locally select the secret value, which is not shared with anyone else. This is really only purely locally used, and then uses this as a key, the secret value, and computes a PRF on the name of another autonomous system. So this is shown here. Then this gives this key X arrow Y, which is denoted like that, meaning that X can quickly derive the key, but Y then has to fetch it, as we'll see in a minute. And so this can be computed within 30 cycles in software. So all the CPUs, ARM, Intel, AMD, and so on, they have an AES instruction that enables computation of AES within 30 cycles. So it's actually around 7 times faster than a DRAM lookup, which is quite exciting. So we always try to avoid any tables, any state, and this prevents or enables the creation of the keys without performing any expensive table lookups. So we'll see how this can be used. So we're forming a key hierarchy using these symmetric keys by key reapplying this PRF function or this AES function. And so we have a first level where we derive a key for every other autonomous system. And then from that key, we compute another PRF based on the host address to then give us a unique key for that specific host. So with this, the disadvantage of this approach is that each entity actually has to fetch these first level keys. So there's SCION has a public key infrastructure, a control plane PKI, which allows you to authenticate each other, and that allows the setup of secure channels. And there's a key server infrastructure similar with the path server infrastructure that then fetches these keys once a day because they change every 24 hours. And so these keys are being distributed in this manner through this key server infrastructure. And here's an example now how this can be used to provide error message authentication at interdomain scale. So in this example here, the source created a packet that created an error at router B in ASB. And this router can now compute a unique key for that sending host using this DR key system, as it knows the local secret value. And so it performs 2 computations of AES to derive the key, and then can authenticate the network packet, sending this back to the source. Now the source has to locally fetch this key. It has to locally contact its key server, which then has this first level key that it fetched from ASB. And then it can derive the key for that host and provides it to the host, and then the host can verify the message. So of course, these keys will be cached. And so this essentially provides a fast way to perform the operations where it needs to be fast, but at the end host, it's okay to contact the local server, which takes a few milliseconds to then fetch a key because it's not so performance relevant at that part of the spectrum. But so now using this technique for the first time, we can have authenticated error messages. And this is really exciting because routers can, using this approach, can now for the first time at very high speeds authenticate these error messages. But you can do a lot more with this DR key infrastructure. And in SCION, we have a lot of systems that use exactly this construction. So one construction is also this epic system, which stands for every packet is checked, which enables source authentication by routers and also path validation by the destination. So this also can prevent a lot of attacks, and it's also really exciting that now in less than 100 nanoseconds, and in hardware probably less than 10 nanoseconds, a router can authenticate the source address of packets. So this is really possible at line rate. And what's exciting also about Epic is that each packet has a unique value, so that even malicious router in the network cannot replicate and cannot say DDoS someone by copying these Epic packets. So we find this is really exciting because in hardware you can actually compute AES in roughly 1 nanosecond, which is really fast. And so this is obviously faster than the memory lookup, and so this is quite exciting that we have now a system that enables these really strong security properties in the network at almost negligible cost for forwarding. And there's two ways to use this in SCION. One is also to have packet authentication. One is through an extra option header. This is called the SPAO header. Or then if you use the Epic system that has a different format for the data plane, which then has these additional properties that are being achieved. All right, so next I'll talk about the use cases and deployments. And in the beginning, we worked on SCION for a long time. And in the beginning, what then really caught people's attention was the fact that SCION enables the secure communication between a set of entities without creating leased lines. So it's a public internet connection. You can get a SCION connection, but it then behaves similar to a leased line to all the other destinations. And so it has distinct advantages over VPNs or over leased lines that was then perceived. And it was exactly this use case of a communication among a community that has then led the Swiss finance ecosystem, and in particular the Swiss National Bank and SIX, which is the IT provider to the Swiss finance industry, to decide to make use of SCION for the communication between the Swiss banks. And this was a project that started in 2015, and they then moved ahead into production with the first use case in 2017, and have been testing the system for the many years between 2017 and now, to then decide last year that actually the finance IPNet will be turned off and will be completely replaced with this SSFN system, which is essentially a SCION-based isolation domain. One of the main reasons to do this was also this governance structure. So they created their own governance domain or isolation domain for this banking ecosystem. And today, this is already in production with more and more banks joining until later next year when the current finance network will be turned off. So this use case has then driven the deployment of SCION within Switzerland, and is also now driving deployment of SCION outside Switzerland, in Europe and across the world. And so the production network has been growing, and what was important was that this was not an overlay and was never an overlay network, right? This was really native network from day one, meaning there was and there is no dependence on BGP anywhere in the SCION production network. Right? There's some leaf nodes that may get the connection via making BGP dependent, but the whole core, and what was important for all these security use cases, that there's really absolutely no dependence on BGP. And so with this, and also with these use cases being rolled out, there's more and more entities that came on board and are expanding the SCION network today. And most of these entities have official products, so they all have native SCION network and are part of the SCION production network. But most of them, they have an actual SCION service you can purchase over regular sales channels that then will give you the SCION connectivity to the end domain. So with this use case being built up, the healthcare ecosystem that was in Switzerland that's managed by a company called HIN, Health Infonet, which is the IT provider for over 50,000 doctors. They've been looking for ways to defend against DDoS attacks and getting a secure connectivity to their doctors' offices, which are typically very small entities. So you cannot have a lease line to all these entities. And when they discovered SCION within a year, they made the decision to create an SSHN, so a secure Swiss healthcare network, and move 50,000 doctors onto this network. And this is in operation today. So they have 50,000 doctors that are now communicating with HIN and the HIN services over the SCION network. And the way this was possible within such a short amount of time is through an infrastructure that is called the gate infrastructure that essentially attracts IP traffic that can be delivered via SCION to a destination, convert it to SCION, and then make use of the SCION network to deliver it to the destination. So in Switzerland, several entities have set up this gate infrastructure, which now collect all this traffic as close as possible to the end user, to the doctor office, and now delivers it via the SCION network to the data center of HIN. So also I've been talking about the university network. This is essentially also part of course, the SCION production network. It's all the same infrastructure. And we're now starting to sign up more and more universities to connect to this, which then also has the entities obtain native SCION connectivity without any dependence on BGP. So what's exciting about this is the simplicity to set this up. Because when you think about a next generation infrastructure, you think, okay, we have to change all the switches or pull new cables and so on. But in fact, it's actually quite lightweight. So in the example of a university, you can get and install a SCION router that communicates with the local NREN offering SCION connectivity, and we're trying to avoid this going through an IP connection to the first SCION provider. But in some cases, that may be a pragmatic way to get started if security properties are not as important initially. Then within the university, there's a control service which hosts this path server. I talked about the beacon server, also the key server, and that is internally reached via IP. So a host that's being bootstrapped with a piece of SCION-enabled software can automatically bootstrap and then can directly send packets to the SCION border router. And so essentially the local IP network is just used as a layer 2 in a way, right? So it's not, I wouldn't say this is an overlay because it's just using intra-domain networking. So it's not making use of BGP. And so this works natively directly from a host where the operating system is unaware of SCION. So to give an example, and here's before the example, here's the current research and education network as it's expanding, which is quite exciting to have a number of entities that either are already or will become part of the SCION network. And I hope many of you here will say, yeah, that sounds great. Let's try to connect as well and get native SCION connectivity for the university. So what's exciting is that with simple software update, you can make use of this natively in applications. So here, the team wrote a Chrome extension And this works on Mac OS, where now, for instance, the ETH web page is available via the SCION network. So here you can see only the ETH web page itself came over SCION, and the JavaScript and so on came from other servers that were not on the SCION network, but it still just works. Here's the web page of David Hausherr's group at Magdeburg. There, everything came over the SCION network, all the way from Magdeburg to Zürich in a native BGP-free manner. People also set up a mirror for kernel.org. And the system tries to see if it can fetch pages via SCION, and if not, it just fetches them over IPv4, IPv6. And for the user, this is quite seamless. And what's exciting is that for, say, security use cases where you need to, say, have compliance for medical data, for instance, that are accessed through a browser, you can now use this environment to have high compliance that the data doesn't leave a certain jurisdiction, for instance, which for some medical data that is required. And so you can use this system today to make use of that. So also with respect to incentives and also with the deployment, you see the ecosystem has been growing, and there's a SCION association that nurtures this ecosystem of different universities, research institutes, but also ISPs or corporations, consultancies. There's a lot more than what's shown here. Entities that are providing consultancy services directly for SCION, actually, and also many more companies than what's shown here. And what's exciting is that AWS is going to make an announcement this or next week that they're SCION enabling and providing SCION access to their cloud services, which is going to be quite exciting. So looking at these real-world deployment incentives, we find that the security aspects and also these governance domains aspects were the main reasons for these first ecosystems, the finance ecosystem and also the healthcare ecosystem, to start. The sorry, electricity providers are also now starting to make use of a SCION network for communication between electricity companies. And so we see that this provided the initial incentives to get started. And now the university networks we have with Princeton University, University of Virginia, Magdeburg, ETH, and additional ones in Korea and Singapore, Hong Kong coming online, that already today, with the ones already connected, we have over 100,000 users that are in a SCION capable network. So if any of these users installs the SCION native software, this will immediately start to work. They can immediately send native SCION packets that get to the destinations without any dependence on BGP. So this is quite exciting, right? So we've seen these advantages. So to step back, so who is our SCION's parents? Well, I guess it's we can have kind of a more modern type family with many co-parents. And so one way to look at it is the community is one of the parents, all the developers and the whole team that has been working on SCION over all these years. But we're still far from being done. So join the fun. I think we've only just started. There's a lot of research opportunities now that the network is operational. You can connect to it and start doing additional research based on all these path diversity and all the security features that are now present. Right. So with that, some resources you can look at. And so in summary, our goal is to keep expanding this network and make more and more real-world use cases to make use of the network. And what's particularly exciting is there's native SCION applications emerging. So some of the banks in Switzerland are starting to build SCION directly into their applications for customers already. So because in Switzerland, it looks like Swisscom and Sunrise will turn on SCION in their 5G networks. So meaning any cell phone can natively communicate through the SCION network. Then obviously the number of users will be several millions when that happens that have access to native SCION connectivity. But even without that, we're trying to expand the university network so that we'll have on the order of 1 million hosts next year on all the different universities that are connected natively, which should give enough of a critical mass to then incentivize application writers to, besides IPv4, IPv6, also provide SCION connectivity to then switch whichever is best to optimize application performance. So with that, invite you to join the network, join the fund. There's some additional information at these URLs. With that, thank you, and hope we have some time for questions.
Thanks. So very, very cool talk. So while we wait for the audience brain to warm up and start with making questions, I'm gonna start with one. Want to challenge you a bit, but you know, in retrospect, seeing a new internet, which is cool, which is scaling a lot, is growing. It's very nice. It reminds me of, you know, the old days of the internet. And when you start scaling, you will see problems that were not precedented. So for instance, I don't know, DNS, because it was not scaling, so we had to change the infrastructure. Path properties you were showing are really nice because already with setup, which is not yet at the scale of the internet, there's a lot of path diversity. So path diversity for sure is a blessing, but can you think that it's going to become a bottleneck? So like for instance, path selection or so, can you comment on this?
Right, that's a very good question. Actually, initially, when the beaconing was not that smart, we did notice, even though the network was still small, there were already signs that the beaconing has to be smarter, right? So the system, and we're still refining this, and I'm sure there's a lot of research that still that needs to be done to do this. The nice aspect is that the control plane is really separate from the data plane, right? So if you have the beaconing, meaning you can have different layers of beaconings. You can have a basic layer that just provides the basic connectivity. So to make sure any two hosts on the internet have at least one path, but then you can add additional paths, right? And you can also prioritize destinations that don't have any path set, so you rapidly discover new destinations, and you rapidly also recover from links that failed to then. But there's different ways to deal with link failure. But one way, in addition, is to push additional beacons. And so the point is, you can have these different layers of the beaconing process, a basic connectivity layer, but then added value layers, so to speak, that finds additional paths that provide more diversity or better properties in some metric. And so the point is, you can customize how much work you want to do to perform this beaconing. And those paths are valid for 5-6 hours. Over time, you will learn more and more paths. But as we've seen, the overheads are really extremely low compared to standard BGP. And so we think this will definitely continue to scale also as the SCION network expands. But the point is, it's customizable how much work one wants to do to have more path diversity. It's a very good question because some of these issues already did come up, right? And we had to change the mechanism to deal with these issues.
Yeah, and 2 orders of magnitude with respect to BGP-SEC is a good head start in terms of margin of computing advantage with respect to BGP-SEC. So yeah, there's a lot of slack. I don't see heads, so guys, don't be shy. Oh, yeah, there's one hand over there.
Hi, Adrian. Fahad Doger Tufts. It's great to see a project that started in front of me as a grad student, still going strong, having so much real world impact. I have two questions, both related to the journey, like the evolution over the 14 years of this project. The first one is, what are the lessons learned? Any incorrect assumptions you made? Any mistakes? And the second one is, over the 14 years, the technology, the application scenarios have evolved too. There is a lot of reliance on the cloud, the flattening of the internet, a lot of the traffic going to a nearby cloud, and then these cloud providers using their wide area network to get to the long haul. What opportunities and challenges do you see in this evolving internet with a more flattening and over reliance on the cloud?
Right.
Thanks.
Yeah, thanks, Fahad. Yeah, very good question. So the first question was about the lessons. So of course, there's been a lot of lessons, but one of the core lessons is really for the deployment. One, as a researcher, I always thought, okay, you create a system that has nice properties, and the practitioners will also see these properties. They will come up with business models and deploy it. And this was quite a surprise that the uptake has much been more slow, right? So typically going to the incumbents, they were not too excited about deploying new systems because they have already well-developed markets, well-developed products. So especially SCION can be seen as quite disruptive by some account managers. And so they fear, okay, if the DDoS defense is already built in, if you have all these optimization properties, if you have this transparency, maybe the customer will see that the connection will be faster through another ISP and so on and so forth. When you get all this transparency, some ISPs may fear they may get a disadvantage. And so the big lesson was to think much further. So it's not enough to just come up with the property and then think people will jump on it. One really has to analyze, okay, how does a company make money? And now how can my system enable enable this entity to make more money or to have a new business model that allow them to gain market share, because that's what everybody tries to do. And so that was really a big surprise, because I was naively thought, well, you build it and people will come, they will see the advantages. But really, it all the way to the deployment, right? Even if the customers deployed it and they had fantastic results, and it was black and white, how much better the system was and the performance and everything. But even that was not enough, actually. One really has to take the additional steps and work out what the advantages are all the way to the business model, how this could look like, how much money one could make. And then typically go to the number 2, number 3s that want to compete with the number 1. They were much easier to convince to try new technologies. Your second question was, if you just give me one keyword, the flattening, right? So yeah, if you look at the amount of traffic, it obviously, more and more of the total traffic volume is going to the core, right? It's Netflix, YouTube, and these kind of services. So if you look from that perspective, it seems, well, inter-domain doesn't matter anymore. But if that it's really though an artifact of these video streaming applications. If you actually look at total amount of traffic going, globally across the world, there's still obviously huge volumes that do not go to the local data center or do not go into the cloud. And many of this traffic is security sensitive, and that that will remain for a long time a very important application. And so if you look from that perspective, all these entities, they really want better path control, better reliability as well. With the multipathing, you get much higher reliability, resilience to link failures, the rapid failover to another path, for instance, and so on and so forth. All these advantages are really significant. even if you look at connectivity to the cloud, there are measurement after measurement that demonstrates that there's a heavy tail that still, despite 1,000 data centers and a lot of connectivity, but still, when you take a customer, many times the internet is not doing and is not providing the best connection. And in a way, it cannot, right? A single path internet, you simply cannot anticipate all the different metrics one would want to optimize, right? It's from latency to bandwidth to jitter to loss to jurisdiction to whom you don't want to go through, et cetera, et cetera. There's so many different aspects. Even for those cloud use cases, we believe that SCION is a great use case. Imagine you have a VPC or a VM in the cloud, and you want to communicate with the corporate headquarters, right? So you can say, well, the internet is doing the right thing, but it may be that you're on a path where somebody's bursting traffic, and now you're starting to see high jitter, packet loss, and so on, and you have to wait, right? Even though Azure is doing every 5 minutes a recomputation of all their paths, well, you may be waiting a minute or two until the situation gets better. In a multipath setting, if now with AWS offering SCION connectivity, the end VM can have different paths and then dynamically switch to optimize and even perform ingress path control, right? You may be saying, or have an interface where you ask AWS, give me an additional path, say that ingress is in Paris or ingress is in Frankfurt or London or at this data center. And then you can even move traffic to ingress at a different location. And it gives so many opportunities that also in these kind of use cases, there's just, it's a better world than having a single path internet.
I have 3 questions. The first question is, if I understand SCION correctly, the main difference with the internet is that it's routing based on AS number rather than BGP. So what is the key benefit of doing this? This is the first question. The second question is that I would think that there are far fewer SCION router than the normal internet router. So a packet go from one SCION router to other SCION router will have to go through the normal internet router. But you said that it's not overlay, so I please clarify that. And the third question is that, do you define any protocol in this thing? If there's new protocol, is it completely proprietary, or do you standardize it in any way?
Right.
Thank you.
So let me answer in the reverse. So about the standardization. So IETF just happened 2 weeks ago, and we submitted a complete set of specifications for the entire base SCION system. So this has been going on for quite some time to have this be an open process, and anyone who wants to contribute can participate. And essentially, the SCION Association, now that it's formed, has an open process where anybody can contribute and participate. So there's no patents on any of the base system in SCION. It's all open by design, and so the plan was always to have this be owned by the whole research community who can contribute and improve the system. The first question was about, the second question was about the number of SCION routers is small. But if you look at the ISPs that are deploying, for instance, Swisscom has a SCION router in LA, in Singapore, in Frankfurt, but all these connections are their own layer 2 connections inside, in a way, as part of their own network. So there's no reliance on BGP for Swisscom to send a packet from Bern to LA, because it's inside their own, so to speak, network with their own fibers that they purchased. So even though the network is, of course, much smaller, But all the ISPs that are peering, they're peering at locations where they have joint routers. So for instance, Hong Kong, Seoul, Frankfurt, Amsterdam, all these places have several SCION routers where the ISPs come together and then do the peering. SwissIX already has a SCION peering offer, and there's additional ones coming at other IXPs around the world. So this is really a native network. There's really no dependence on BGP. Your first question was about AS.
Routing, but AS number routing.
Oh, right. So I think the main difference really though is the path-based architecture, right? That these path segments that are being created, they're AS-based, but the path diversity is larger than just AS to AS because the interfaces between the ASs are also being identified. So if Swisscom or Switch and SCION, they have a SCION router in Paris and in Geneva. So you can see if I go from ETH to Magdeburg, I can send it through the SCION router in Geneva, or I can send it through the SCION router in Paris and then go to Magdeburg. So I'm getting that level of path diversity. And it's really these path combinations that make up the good properties of SCION, right? These path segments that are created in a way that there is always that you're guaranteed to have a connection between any two hosts. Because if you look, there's been many path-based architectures, and a challenge always is you may have a lot of paths, but how do you get a policy compliant path, and how do you get an actual end-to-end path in the end if you have a sea of path fragments or path segments? The way SCION is constructed, it just has this guarantee that there is always at least one combination. And that's, I think, some of the difference that then gives all these nice properties.
If nobody want to ask question, I will ask another one. Just now you talk about SSFN and SSHN. What's their relationship with SCION? Are they over SCION, or are they different networks?
These are isolation domains or governance domains that are running SCION internally. Right now, to start with, they're still separate because they're bootstrapping these networks, but the plan is to connect them also to the global SAN network. And also with the energy sector is now coming, and other critical infrastructures as well. They want their own governance domains, their own isolation domains, but we're trying to point out that the security mechanisms are already there in the regular isolation domains. So, but that's something we're trying to steer a little bit. But it seems that this is really also the feature that they want to provide a way to govern the ecosystem and issue these certificates and having control over that for these highly critical applications.
And indeed, speaking about reason of success, so to shift from technical to more broad view. So you mentioned indeed the fact of having the total ability to build an island with local governance. Earlier, you mentioned practitioners, and again, about sovereignty. This was surely factored in the very early design. But did you find something that was unexpected and led to a success because you may not have thought everything from the start as important, and then it has an importance practical?
Right.
So if you can comment on this.
Right. Yeah, there's I always thought this geofencing, which means that you can control traffic is not leaving a certain area, is nice, but it seems that it's becoming a critical property for some entities now. Also, the fact that these isolation domains or governance domains are being used for traffic compliance that themselves, and not just the path aspect that you can make sure traffic doesn't leave a certain AS. That was also surprising that this has become a lot more important over time. The original thought really was to have this trust scalability, and observing current trust models issues, but now it has really become actually the main reason for these first deployments, and that was definitely a surprise. That's maybe the main one of the main surprises, right?
Hi. So very interesting talk. Thank you. I have a question. In the beginning, you said that our PKI has problems. However, our PKI is used on the application layer, right? So as a user, I'm interested into like connecting to the right service. I'm not really interested in if I'm connecting really to a certain IP address. It's like imagining CDNs, they're like an abstraction layer. So I'm interested in, is the one I'm connecting to actually offering YouTube, etc. So do you solve this?
Right. So it's a very good question. So the observation is that you have PKIs at different levels, but so in SCION, what this end host authentication gives you is then have the intermediate systems being able to benefit from it, right? So if you have a DDoS defense system, it's really useful to know somebody cannot spoof source IP addresses anymore, or it's very useful to have, say, a high-speed firewall that allows you to authenticate and being able to state, okay, these entities can connect to then use these lower level properties. Now, the higher level ones, like you're pointing out, the actual data download from a CDN or a web page, then has a different level. But in order for all that to work, for DNS to work reliably, preventing DDoS attacks and so on, you can then make use of these lower level systems internally to then derive and make the high level systems work much better. Right. So as security practitioner designing various systems, if you want very high security, you also assume that part of your network is actively malicious. So you have malicious routers, you have malicious autonomous systems, malicious ISPs, and so on and so forth. Then it gets really complicated because they do see a legitimate packet. So now how do you ensure at very high speeds that this router cannot just replicate these packets and still flood the destination, right? So that's where the importance of then these lower level systems come into play, so that you can then also achieve properties for the much application level systems.
Thank you.
Right.
Time for question. Question would be a recommendation for students that want to work on improving. So instead join. So for instance, if your PHP detecting is no longer a problem. Science. So what are the limits of the where we need more brain power?
I think all the aspects. I think we're still working on the internet as well. So I'm sure these ideas can be used and can be improved, can be extended. But I think a really exciting question is to try to figure out how to get more performance now that we have a huge path diversity, right? So what type of information, who collects it, how is it being distributed? Should it just be piggybacked on the beacon, but then after 5-6 hours, it gets stale, obviously. So should we have yet another infrastructure? And so which information do we collect? How do you trust it? I mean, there's just so many. I joke, there's, about 20 PhD theses just in this question alone, maybe even more. It's just an enabler for doing things in a different way. Yeah, it's. I think there's a lot of such exciting topics, especially also security. There's now new building blocks. Now, how do you make use of these building blocks to build higher level properties? I think this these type of path-aware networks they are actually an enabler for a lot more work to become feasible. So that's the hope that we can increase the size of the community and improve our current networks based on ideas in this direction. Right.
Doesn't seem to. Okay, now it works. So I think that's I want to join everybody to welcome again Adrian for the very nice keynote today.
Great, thank you.